Hello, in this video we're going to be talking about the tangential and normal components of acceleration. So, just to review some of the things that we've talked about and to show you some formulas here that we're going to end up with. We're going to let speed be the norm of the velocity vector, and we're going to represent that with a v with no arrow. V with the arrow is the velocity vector. Little v with no arrow is the speed. Some people used, instead of the arrow, they'll use a bold face for the vector and then a regular face for the scalar. The unit tangent vector is a vector in the direction of the velocity but of length 1, so you just take the velocity vector and divide by the speed to get that, which means that the velocity vector is a scalar multiple of that unit tangent vector, and the scalar multiple, of course, is the speed. One way to write the formula for the curvature is the norm of the derivative of the unit tangent vector and then divide by the speed. Okay, and solving that for the norm of the unit tangent vector, it is the speed times the curvature. Now, the acceleration is the derivative of the velocity. So if we think of the velocity in terms of this expression here as v speed times the unit tangent vector, we can apply the product rule. So it's the derivative of the first part times the second plus the second part times the derivative of the first. I think I said that wrong. Derivative of the first times the second plus the first times the derivative of the second. That's one way to say it. Okay, so in any event, this is, you get this expression right here. So notice that this is a component in the t direction, and we'll show, and this part over here, I want to look at it a different way. I'm going to multiply the second factor here by the norm of t prime over the norm of t prime. Of course, we're multiplying by 1, so that's equivalent. But this t prime over the norm of t prime is our unit normal vector, n. And then we have let's see, this expression here, t prime norm is v times kappa. That is the speed times the curvature. So I replace the 1 in the top by v kappa, and this t prime here divided by the norm of t prime by the n vector. So this velocity or speed times the curvature times this speed gives us the curvature times the speed square. Now, this t vector and this n vector are perpendicular to each other, and so we've broken this down into perpendicular components. In other words, we've broken down the a vector into the sum of two perpendicular vectors. The first vector is this vector here that's going in the direction of the speed, the direction of the motion, direction of the velocity, and the second component is perpendicular to that. So this first part is the tangential component, which is the magnitude of that, which is the derivative of the velocity, and the second component, the normal component, is, or perpendicular part, is the curvature times the speed squared. Here's our picture here in a two-dimensional example, showing we have this curve tracing along here as time goes along. At a particular point here, this blue vector is our position vector, the velocity vector is here, the acceleration is here. And then we take the acceleration and we break it down into components in the direction of the velocity and perpendicular to it. Those are the two components we're talking about. So this vector here is the v prime times t vector, and this orange vector going perpendicular to it is this curvature times the speed squared times the normal vector n. And so we get that. They're not always vertical and horizontal components, but they are components. It does turn out, however, that these components are always in the same plane as the normal and the t vectors, as you can see here. And so we don't get acceleration in a different plane. It's in that same plane with those. So summarizing some of these results, okay, here you can see the formulas we came up with. The acceleration vector is the derivative of the speed with respect to time times the unit tangent vector plus curvature times the speed square times the unit normal vector, so that the v prime is the component of the acceleration that's tangential or in the direction of the motion, and the curvature times the speed square is the component in the normal direction. So acceleration is always in the osculating plane that contains the unit tangent and principal unit normal vectors. So that's an important result. The tangent component of the acceleration, tangential component, is the portion of the acceleration which has a tendency to speed up if it's positive or slow down if it's negative, the speed of the object in motion. Its size is just the derivative of the speed. Now when we study motion in a straight line, that was the end of the story for acceleration because everything was in one direction. Okay, the only directions you had were basically forward and backward, speed up and slow down. But when we allow our motion to go into 2 or 3 dimensions, this normal component of the acceleration comes into play. And the normal component of the acceleration is the portion of the acceleration which has a tendency to redirect motion, making it turn more in the direction of the normal vector. So this normal vector is pointing to the left of the direction of the motion here. If you're pointing in the direction of the motion, that's a left turn. And notice, of course, that if you're following this path, you'd be making a left turn. Okay, or at least curving to the left. So in an automobile, for example, we control these components with some simple controls on the car, right? And so the gas pedal or accelerator and the brake are controlling the tangential component. They also have some effect on the normal component, but it's controlled large part by the steering wheel. So on the normal component, notice that it is the curvature times the velocity or the speed squared. Curvature times speed squared is the normal component, the size of that vector portion of the acceleration pointing perpendicular to the motion. And it's the curvature times the square of the speed, that should say. Let me fix that. Okay, so again, let's think about if we're going around a sharp turn in a car. So if we have a large amount of curvature, that's a tight curve, that's going to increase the normal component of acceleration, possibly throwing the passenger against the door as you're going through that tight curve. But also notice if we double the speed, the normal component of acceleration is actually multiplied by 4, so the speed has something to do with this normal component as well. And that's going to also have a tendency to throw you against the door. So you could have the same curvature, but if you're going around the curve really fast, it's going to have a tendency to make the car or the passenger slide out. If you have, let's see, if you have a larger speed with the same curvature, that's going to do it, or the same speed with a tighter curve, it's going to have more effect of throwing you out to the side. So let's look at an example, get our hands dirty with some formulas here a little bit. This is an example of a particle in motion that we looked at in an earlier video, and we already worked this part out, so let me remind you of what we had. We had the r, or position vector, was t squared, comma, ln of t, comma, t times ln of t. So this was the vector position function. The derivative of that is the velocity vector, that's v of t or r prime of t, and that was the vector 2t, comma, 1 over t, comma, 1 plus ln of t. Then the acceleration vector is then the second derivative of the position, or the first derivative of the velocity, and that's going to be the vector 2, comma, negative 1 over t squared, comma, 1 over t. The speed, v, is the magnitude of the velocity, which is the magnitude applied here, so square each of these three, add them up, and square root, and we simplify just a little bit to get the fraction with t on the denominator, and the numerator is the square root of the whole thing, 4t to the fourth plus 1 plus t squared times parentheses 1 plus 2 natural log of t plus the natural log of t squared, close parentheses. The curvature gets a more complicated formula. I'm not going to read the whole thing here, but you can see that formula. And there's the unit tangent vector down at the bottom. So again, all the details were worked out in an earlier video. Okay, so let's work out the normal and tangential components of acceleration for this particular one. So the acceleration component in the t direction is the derivative of the speed. So there I just copied the speed formula from the previous page as a function of t. Now notice that is a function of t, so that speed is, so when we have to do the derivative, we have to have it, in terms of t. Now this is a quotient here, so I'm going to apply the quotient rule. First of all, the easiest part, the denominator is going to be the original denominator squared. Then on the top, we have the bottom times the derivative of the top minus the top times the derivative of the bottom. Okay, so we have the bottom, which is t, times the derivative of the top. Well, this is this expression to the 1/2 power. So it's 1/2 that expression to the negative 1/2, which puts the square root in the bottom there. And then you have to multiply by the derivative of the inside of this for the chain rule. The derivative of 4t to the fourth is 16t cubed. Derivative of the 1 is 0. Now we have a product rule going on here. So it's the first part, t squared, times the derivative of the second. Derivative of this part is 0. Derivative, that's 1 over t, so that's 2 over t for that part. And this is like u squared, so it's 2 natural log of t to the first power times derivative of the natural log of t is 1 over t, so that's 2 over t natural log of t. All of that part there is multiplied by t squared, see that? Plus, what? The second, let's see, this is still within the product rule, right? So the t first, t squared times derivative of the second, that was here. Now we have to do the second, which is this expression here, exactly like it is, times the derivative of the t squared, which is 2t. All of that is within that product rule. Okay, now, so that's the bottom times the derivative of the top. Then we got minus the top times the derivative of the bottom. The top is just there. The derivative of the bottom is just 1, so that part's pretty straightforward. Now this is a big mess, so let's see if we can clean it up a little bit. I've got fractions inside of fractions, so I'm going to get rid of that by multiplying top and bottom by this square root thing here, which is just our original numerator of our speed up here. That's going to cancel this out, and it's going to square out. The square roots are going to cancel out here, and I can distribute the minus. So let's look at the part at the end first. It just has this thing that's under the square root with all the signs changed. So it's minus 4t to the fourth minus 1 minus t squared times this stuff here. Now, I'm also going to take this part here, and I'm going to take the 1/2 t and distribute it across here. So 1/2 t times 16t cubed is 8t to the fourth. 1/2 t, well, I'm going to take the 1/2 t and multiply by this term. I'm actually going to take the t over 2 and distribute, which is going to cancel that and that, 2 over t. So I get t squared times 1 plus natural log of t for that part. Now the 1 over t times this, t over 2, excuse me, times this 2t makes that a t squared, and I still have this factor here. Okay, and of course this square root, since I multiply top and bottom by the square root, is going to be down here with the t squared. All right, let's do just a little bit more cleaning up. 8t to the fourth minus 4t to the fourth is 4t to the fourth. And then this one, and this one all have t squared, so I can factor that out. And I'm left with, let's see here, I've got a 1 there, plus 1 more there is 2, minus 1 there is 1. I've got a log of t here, plus 2 more log t's is 3 log t's, minus 2 log t's is 1 log t. And here I have a plus the log of t squared, and here I have a minus log of t squared, so that cancels out. And then I have, let's see, that was that term, and then I have a minus 1. That term should, let me look at this a minute. Okay, that part shouldn't have been there, so that's something extra left over from some copy and paste or something. So anyway, this is the formula for the tangential component. And the normal component is just found by multiplying the curvature, which is this formula here. Kind of nasty, but there it is. And the square of the velocity, or square of the speed. The speed was this part right here. When you square it, the square root goes away and the t goes up to t squared. Okay, and I'm not going to attempt to try to clean that up any at the moment. We're just going to leave it like it is. Okay, I guess we could, one thing we could do is probably put this part here with this and make it to one power. I guess it would cancel that. Actually, let's do that. That's pretty easy to do. Okay, so that simplification is pretty easy. There are basically 3 of these square roots multiplied here. This is like 2 of them, so that cancels out that down to the first power, or this is this expression to the first power. This is the 3/2. Subtract exponents, you get the 1/2 power in the denominator. That t squared cancels that t down to 1t in the denominator. So that's a little bit of a simplification. It's easy enough to do. So there is the normal component as a function of time. Okay, now if we look at these at a specific place, say t is 1, we can plug this in. So here you see we took the formula from the previous page and just plugged in 1s everywhere we saw a t. And remember, natural logarithm of 1 is 0. So this is 1 times 1 is 1, minus that 1 is 0. 4 times 1 is 4. So that's 4. That's 1, of course. Then here we have 4 plus 1 is 5. Let's do this. That's 0, 0, 1. That's 1 times 1 is 1. 5 plus 1 is 6. So that's the square root of 6 at the bottom. So it's 4 over square root of 6, or if we want to rationalize the denominator, multiply top and bottom of that fraction by square root of 6. That gives us 4 square root of 6 over 6. The 4 over 6 reduces to 2/3, so that's 2 square root of 6 over 3 for the tangential component. The normal component is this formula that we had here and plug in 1 everywhere. And if you work that out, again, this denominator is the same expression we had right here. So we already know that's the square root of 6 times 1 is still square root of 6. And we have to work this out here. So there's a 4 plus 0 plus 0, still 4. Another 0, that's still 4. And in 16, that's 20. So it's the square root of 20 over square root of 6. Or we could just plug in what we had done earlier for the curvature and the speed. The curvature was square root of 30 over 18 from a previous video. We worked that out. And the speed was square root of 6. Of course, you square that, you get 6, cancels the 18 down to 3. That's the square root of 30 over 3. You can multiply top and bottom by square root of 6 here and simplify this radical of the square root of 20. And it also turns out to be square root of 30 over 3. So this is correct either way you do that. Okay, so here is the picture of what this looks like. Here is our curve once again. We saw this in an earlier video. It's a curve in space. And here's the point here where we have our, when t is 1. So that's the vector going across here to this point here. It's at 1, 0, 0. And you can see the unit tangent vector here, the velocity vector there. The normal vector is kind of coming out this way. In that plane is where we see the acceleration vector, which is coming out here toward toward us. It's kind of this maroon one here. The binormal vector is going down here. So you can kind of see some of those things. It might be better with a different view, but anyway, that's what we get. So we found from what we just seen that the tangential component is 2 square root of 6 over 3. The normal component is square root of 30 over 3. The unit tangent vector is 2 over square root of 6, comma 1 over square root of 6, comma 1 over square root of 6. The normal, unit normal, well, I'm going to show you a way to find the unit normal. We could do it by taking a derivative of that unit tangent vector. Let me show you what that would be. So the unit tangent vector is this formula. We'd have to take a derivative of that. And then once we found that derivative, we would then turn around and divide by the norm of that derivative, and we should get some functions a, b, and c. Okay, and then we could plug in t equals 1 and figure out what it is. Well, certainly I could do it that way, but that's a little messy, and I'm going to avoid that right now because I know that I can just, since I'm only interested in one specific one, I've got enough to figure that out a different way. I know this acceleration vector at 1, we already know what it is. It's the vector 2, negative 1, 1. And it also has to be this 2 square root of 6 over 3 times the unit tangent vector, which we also know, plus the acceleration component in the normal direction, square root of 30 over 3, times a, b, and c, which are functions of t. I just dropped the of t there. And I just need to solve that vector equation. First of all, notice we have these 3's here, so I'm going to multiply both sides by 3's, which is going to leave this 2 square root of 6 and this square root of 30, but it's going to triple everything here, so that makes this 6, negative 3, and 3. Then I'm going to take the 2 square root of 6 and distribute here. The square root of 6 is going to cancel all the denominators, and that is double the numerator, so I get 4, 2, 2 for this vector here. And then, of course, I have square root of 30 times this vector ABC. Now I subtract 4, 2, 2 from this, so that gives me 2, negative 5, 1, and then divide everything by square root of 30 to get the normal vector right here. That's a good form to put it in, or if I rationalize denominators by multiplying square root of 30 over square root of 30 times each piece, you get it in this form here. So the final version I have there for the unit normal is square root of 30 over 15, comma, negative square root of 30 over 6, comma, square root of 30 over 30. And you could verify, which I did with the calculator, that this is a unit vector. And you could do the dot product of it and this tangent vector here and verify that that is in fact 0, so that it is orthogonal to that. And so that should be the brown vector that we have here. Okay, this unit tangent, this one right here, is the purple vector here, this way. Okay, and of course these components, if you take the this part right here, the 2 square root of 6 over 3 times this unit tangent vector, if you take that term, that's going to be a component of this acceleration that's going in this t direction. And there's going to be a component going in this brown direction, which is going to be, the component is the square root of 30 over 3, but the whole vector is the square root of, is this vector right here that we ended up at the very end. Okay, so there's an example of working out, finding the tangential and normal components of acceleration.